Hello everyone, welcome to this tutorial about asynchronous programming in Python. Asynchronous programming, which is also called as concurrent programming or coroutine, is one of the new concepts introduced in Python. So in this tutorial, we are going to explain the architectural principles behind the asynchronous programming. So we will be more explaining about how Python is implementing this asynchronous programming or coroutine or concurrent programming. So we will be focusing about the behind the scene activities of asynchronous programming, like how PVM, Python virtual machine, handling the multiple coroutines, how the interpreter running multiple concurrent programs at same time. So we will be focusing this type of concepts than the syntax of coroutines. So all these three terms are same, coroutines and asynchronous programming and concurrent programming. These are the same concepts in programming languages. So um, I will be explaining these concepts with the help of asyncio module of Python, which is the default module of Python that supports the coroutines. So additionally, we will be covering the event loop that are used to run the asynchronous programs. So let's move into our next slide. So in this slide and in some of the upcoming slides, I'm going to explain the difference between sequential way of execution and asynchronous way of execution. So in Python by default, um, all the programs are executed sequentially. So instructions and tasks or functions are executed one by one. So a program in Python will be having a lot of instructions, functions and all. So each of these instructions and functions are executed one by one sequentially. And by default using Python is using a single process and a single thread to execute the program. It is the default nature. So sequential way of execution is happening in Python by default. Asynchronous programming and asynchronous way of execution is a new concept in Python. So we have to write our program in that specific manner, then only that program will be executed in asynchronous way. So in this slide and in some of the upcoming slides, I am going to explain the mm, difference between this sequential execution and asynchronous execution. So I am going to explain these concepts with the help of a burger shop example as you see here. So um, what you are seeing here is a burger shop example, a simple burger shop example, and this example is picturized to describe the sequential way of execution. And in the next slide, I will explain the asynchronous way of execution. So in this particular example, you can see they have a kitchen. So the food is actually cooked inside this kitchen, and they have a reception here or counter here, and a counter boy is here. So order is actually taken and processed by this reception and reception boy, and they have a queue of customers. They are here to provide the order and to buy the burger. So in normal way of their burger shop's execution, this burger boy is calling each customers one by one and taking the order, and his processing means he's doing billing, those type of things activities he's doing, and after that the order will be sending into the kitchen. So once the order is sent to the kitchen, the cook will be um, cooking the burger, and it may take some time, right? 5 minutes or 10 minutes. In some cases it may take 30 minutes if order is very big. So in that case, in this sequential way of execution of this burger shop, all others have to wait until the order is cooked, order is completely cooked. So the people like the reception boy and the customer who provide that order and all other customers have to wait until this order, right? This burger order is cooked completely. Once it is cooked, he is handovering that burger to this reception, and the reception boy hand over it to this customer, and he is leaving. Only after that, uh, this reception boy calling the next customer. So customer one customer will be called and his order will be delivered, and the next customer will be called and his order will be delivered. So this is the way of execution in the sequential burger shop example. Okay, so you can see this is not fast. The queue will not move that much fast, because if one customer's order is taking 30 minutes or 1 hour, all others have to wait the whole 30 minutes or 1 hour. Only after completing it, the next customer will be called. But it is very simple. The chance to get error is less. The error means one person's bill is giving to another person's, one person's order is giving to another person. So this type of complications will not be will not be there. It is a very simple way of execution. Chance for confusions and errors are less, and this this reception boy is getting a lot of free time, and everyone have to wait. On the other hand, waiting time is very huge, and this queue will be moving very slow. And yeah, so you can see a lot of ways to improve the operation of this burger shop, but we will see those ideas in the next slide. So actually the concurrency or asynchronous programming is to improve the operation, right? This execution speed and operation of this type of a sequential method. So here in this slide I'm stopping by just explaining this uh, sequential way of execution of the burger shop. The next slide I will just connect this example with um, our Python program execution, how it relates and all I will explain. So I'm stopping this slide right here, and I am moving to the next slide. So this slide is the continuation of the previous slide. So here I am trying to relate or connect this burger shop example with a real sequential Python program execution. So I am going to connect each of the elements in this burger shop with the corresponding Python program execution elements. Um, so you can see they have a kitchen. So you can consider kitchen as a CPU core. You can see they have three different core. Nowadays the processors having multiple cores, so you can imagine one kitchen as a one core of a processor. So this is a 3-core processor. So you can imagine kitchen as the CPU core, and this counter you can imagine as a PVM process. So PVM process is running on top of operating system, right? So the Python virtual machine process is fetching the instructions one by one, just like the order is taken one by one. The PVM process is fetching the instructions one by one. So counter or reception and the counter boy, this area you can consider as a PVM process that running on top of an operating system. And these customers uh, that are going to be processed by the PVM process, these customers, they are in the queue, right? You can consider them as the tasks or instructions to be executed. So these are three different elements of our burger shop and how they relate into a Python process, right? A Python way of execution. So they have a normally Python program will be having a set of instructions. So they have to run one by one in sequential manner. Um, and PVM is actually fetching those instructions or tasks one by one, and it will be sent to the processor by this PVM process operating system. Actually PVM is running on top of operating system, so one by one it will be sent to the kitchen. Now I am going to explain how in this sequential burger shop example, how the instructions or the order is operated. So here, as you know, they have a reception boy. He is calling the instructions or the customers one by one. So he'll be calling the first customer. So first customer reaching the reception, and he is giving the order, and the PVM or the reception boy is processing his order and sending that order into kitchen. So in kitchen, this cook is processing this order. He's making the burger. So it will take some time, right? So at that time, all other customers are waiting, including the PVM and the customer who gave the order. Everyone is waiting for the completion from the kitchen. So this is, as you know, PVM process will be running on top of operating system. Operating system convert this task into assembly language instructions, and it send these assembly language instructions one by one in order, and the operating system managing sending this instruction to uh, uh, CPU core. So here you can imagine something like this. In this kitchen, this burger is cooking, and by that time, no, at that time, all the customers are waiting, um, and even the PVM is waiting. And once the uh, operations are over or from CPU core, and it will be passed through the operating system into the PVM process. So PVM is getting the results, and then it is completed. Is giving that order, is delivering that order to the customer, and the customer is leaving. Okay, customer is leaving, and he's calling the reception boy is calling the next customer, and the next customer is also doing the same thing, and his order is also processed in the kitchen, and everyone else is waiting, and once it is completed it will be delivered, and he is also leaving, and the next customer will be called, and next customer will be called, and his order will be also processed here, and others are waiting. So this is the sequential way of execution. One by one the customers will be called, and their uh, order will be processed in the kitchen, and while it is processing, all others are waiting in the queue. So this is a type of inefficient way of executing uh, or operating this burger shop, right? So you can find out many other ways to improve these operations. So we are going to explain it. So asynchronous way of execution is one of the improvement we can do, and it is simple too. So we will see it in the coming slides. So in this slide, I'm going to explain the asynchronous way of executing a Python program. Asynchronous mode is also called as concurrent model of execution or coroutines. So I'm going to explain this asynchronous method of execution with the help of same burger shop example. So in this burger shop example, almost all elements are same as the previous slide. Previously, we were discussing the sequential way of execution. So, in the asynchronous way of execution, also almost all elements are same. You can see they have kitchen, they have a reception staff, and they have a queue of customers. um, they are here to buy the burgers, and additionally you can see a waiting bench is here. So it is very simple here. All other elements are executing same as before, but the only difference is that here the reception boy is more smarter. The reception boy is more smart. So he is very smart, and he is effectively and he is efficiently utilizing his time. So this reception boy means the Python virtual machine. So Python virtual machine is more efficient here. So they have a new concept here called event loop that we will see in the coming slides. So using this concept, the PVM handling the task more efficiently. In our burger shop example, our reception boy is more smart, so he is handling the queue more efficiently. How he is doing that? Because he is calling the customers one by one. We know there is no difference in that. He is calling the customers one by one and taking the order. The only difference is that when if the waiting time of the order is big, then he will ask the customer to wait in this bench, and he will call the next customer, and again he will take the order. If waiting time is small, then he will serve it quickly. He can serve it quickly. Then he will call the next customer. If his waiting time to prepare the food is big, then he will again ask the customer to wait, and he is calling the next customer. And frequently, again and again, he is checking, is the order for this waiting people is ready or not. If it is ready, then he is serving that order, and they are leaving. So as you can see, the queue will not be waiting. If they have a waiting time, he will ask that particular customer to wait in the waiting bench, and he will call the next customer. So it is an efficient way of handling the queue, and queue will not be stuck. It will not be waiting. The queue will be moving always, and this uh, reception boy is actually utilizing his time more efficiently, is more active. So um, as you can imagine, PVM, Python virtual machine, is handling the task more efficiently than the sequential way of operation. But as you guess, it is a little bit more complex because it should be written very carefully, because they have chance for the confusions. Uh, as we discussed before, one person's bill may be given to the other customer, and one person's order he may serve to one another person. Those type of confusions, chance for the confusions are uh, bigger than the sequential method of execution, and the chance to get error is also big and a little bit more complicated for the programmers. So the waiting and who have to wait and who have to served instantly is decided based on the programmer have to decide it, and he have to write his task or his program in such a way. Based on that only the pvm handle the instructions, and the pvm decide which one have to be wait and which one have to be served instantly. So it is up to the programmer. So we will see it in next slide. So in next slide I will just explain a little bit more how this is happening, to make it more clear, and I will connect it with the uh, real Python environment. Okay, so let's move into the next slide. So in this slide I am going to explain the asynchronous way of execution. So I marked here this I previously explained in sequential way of execution slide. So kitchen means CPU core, and the reception or counter means PVM process, and the customers are the task or instructions. So PVM or the counter or reception boy fetch each instructions one by one. PVM fetch each instructions one by one. So in our burger shop example, the reception boy call each customers one by one. So he's calling the first customer. So this is the first customer. He's reaching the counter. He is giving his order. Then the reception boy understand his waiting time is big. So the reception boy send the order to the kitchen for processing and ask him to wait. So he is waiting here. The customer is waiting in this waiting lobby, and after that, so his food is cooking here. His food, the cook is cooking his food here. So at that time, the reception boy call next customer. So uh, next customer reaching the counter, and he is giving his order. Maybe his order may be waiting time may be less, so he instantly serve that order, and he can leave. Okay, so after that he's calling next customer. So next customer is reaching, and his waiting time is also big. He's understanding the PVM or the reception boy is understanding, the new customer's waiting time is also high. So he is also asked to be wait in the waiting lobby. So again and again this this counter boy checking with the kitchen, um, is it ready, is the order for this customer is ready, this customer is ready and all. So if it is ready, if the order for the first customer is ready, he is serving that order, and he is also leaving. So only one person is there, and after that he is calling the next customer. So you can see the queue is moving and there is no waiting period here for the people in the for the customers in the queue. The queue will be always moving, and if it is waiting time is high, then the reception boy asking them to wait in the waiting area, and after that he is checking, is it ready, is the burger ready for all the people who are waiting in the lobby. If anything is ready, is serving that and calling next customer and checking again for the other customer, is their burger is ready or not. So in this way, pvm or python interpreter manages asynchronous programs or coroutines efficiently than the sequential programs. I have to explain one more concept here, and um, that is about this particular area. So, as you know, this is the processor. So this kitchen area represents the processor, and each of this kitchen, right? They have three different kitchen. I am mm, highlighting three different kitchen here. So each of this kitchen represent a core of the processor. So this is a three-core processor, and they have uh, three cores available in this processor. So as I shown here, as I uh, draw here, only one kitchen will be active. The other kitchens are inactive. So this is to represent the Python mode of execution. So in Python asynchronous mode of execution, the Python asynchronous programs are running using single process and single thread. So a single process and a single thread process in Python can only utilize one kitchen. Can only utilize one kitchen. So Python implementing asynchronous programming using single process and single thread, and a single process and a single thread programs in Python can only utilize one kitchen at a time. So this is not a limitation of Python. In most of the other programming languages also, a single process and a single threaded application can only utilize one core of the process. So other cores, other CPU cores will not be utilized in Python asynchronous mode of execution. So as you know, in Python asynchronous mode of execution, multiple tasks are handled simultaneously. So multiple coroutine functions are running at same time, even though it is not handled uh, by different process or different thread. So multiple coroutines or multiple asynchronous functions are handled using single process and a single thread. So let me explain a little bit more here. So suppose you are writing a program main.py. So all of your program, your functions, everything will be written inside this main.py. And if you want to run this main.py program, you are giving a command like python main.py. So Python here is the executable which is responsible to start PVM and do the initial setup for PVM and run your program. And main.py is the command line argument to the Python. So main.py or the path to your Python program will be considered as a command line argument to this Python executable. So when you are running your program main.py using this command, right? Python main.py, what operating system will do? Operating system will create a new process to run main.py. So you are writing a program and after that you are running it using Python main.py. So Python is an executable which will start the PVM, Python virtual machine, and main.py is the program you wrote. So to run this program you have to give something like Python main.py. So when you are running this application, this executable, Python executable with this command line argument, OS, operating system, OS, operating system, create a new process, to run main.py. So this process will be a PVM process, Python virtual machine, right, or Python interpreter. So when you are calling the Python main.py, operating system will start a new process to run main.py. So that process will be PVM process, PVM or interpreter process, right? So this process. So we were discussing about this process when a program is started. We told that one process will be it will be executable. It will be executed using single process and single thread normally. Otherwise, we have to write specific code to start a new process and new thread inside our program. So normally when you are running a Python program, it will create a single process and it will create a thread. So what is thread? Thread is nothing but, for example, you are writing this program, right? So when the PVM started, so what a Python virtual machine will do? It will first compile your main.py program and will create a bytecode, and using that bytecode the interpreter will be starting. So they have two-step process. In the first step, um, the PVM, Python virtual Python virtual machine, compile your main.py. So that is the first step to check the syntax errors and all, and the bytecode will be generated also, and using this bytecode the interpreter will be starting the execution. So we can imagine something like initially the PVM will create a task queue or instruction queue. So we can draw an instruction queue. So here, so suppose this is the instruction queue. So I'm drawing an instruction queue here. Can call it as IQ or insertion queue. So what this process is doing, what the PVM or interpreter process is doing. So interpreter is actually running a loop, while loop. You can imagine this may not be the right uh, uh, implementation, but the method is same. This is how it is working. So we can imagine as the interpreter process is entering into a loop. So while true, and uh, it is instruction equal to pop IQ. So the queue will be popped, and after that the next step is execute. So this loop, right? So this loop is called the main loop or main thread. So this is the thread actually. This process is created in operating system level. So I told that OS create a new process. So operating system can only create a process. Similarly, the thread is also managed by operating system. So the interpreter can instruct how the instructions have to be executed, when the instruction should be popped. Those things interpreter can instruct. But the actual execution of this loop and actual execution of the instructions have to be carried out by operating system. Only operating system can handle it. Otherwise, if individual applications are directly trying to execute, it will be something like chaos. um, Memory management or processor CPU management, and IO management. Um, the each individual applications cannot handle other applications, right? So there should have a central person to manage the entire thing. So that is why OS is very important. Operating system is that central manager of the computer. So operating system start the process, and operating system entering into a loop, and that loop extract the instruction queue, right? They have a task queue, or we can call it as instruction queue or task queue. So operating system is actually popping the task queue or instruction queue that is actually created by Python virtual machine or interpreter. So it is popping this instruction, and that instruction will be executed. So, and once it is completed, the execution is complete, it will move into the next instruction. So once it is this one, right? Once the first instruction is completed, it will go to the next. It will pop the next one, then next one, next one. So this is a loop until it is reaching the end. It will be executed. So this loop is called the thread. So in normal Python, you can create multiple threads. So when you are telling you are creating a thread, you are actually creating one another loop that are going to be handled simultaneously. So you are going to create a new thread parallelly. You are going to when you are creating a new thread, you are going to create a new uh, loop that can fetch instruction from one another instruction queue, and that instruction queue may be defined by a function. So I'm not it is out of the scope, so I'm not explaining that part here. So I will be doing a separate video for how threads are handled and all. So here I am, my focus is um, uh, this main loop, and what is main loop, and what is a process. So when you are writing a program main.py, um, you are writing your functions and instructions inside it, and you are running it using Python main.py. So operating system create a new process to run this main.py. So that process will be a PVM, Python virtual machine process. That is actually the Python executable, right? So based on this Python executable, you will be starting that, means operating system will be starting a new process. So this process will first, right, or PVM, Python virtual machine, is creating an instruction queue or task queue. You can call it as task queue or instruction queue, and the PVM is entering to a loop. We can call it as main loop. So this loop is actually popping instruction one by one from this queue, task queue, and executing it, and after that fetching the next instruction. So this loop, right, this particular loop is called thread, right? So um, um, thread is nothing but a loop that can fetch instruction by instruction and execute it. So when you are creating one another thread, um, you are actually creating a new loop, and that new loop fetch instruction from one another instruction queue. So who is handling it? Operating system is handling it. So threads are handled by operating system directly. The main loop, and if you are creating one another thread inside your program, um, internally you are calling a system level function to create a new thread. So operating system will create a new thread. So new thread means it is a new loop, something like this main event loop. You are parallelly creating one another loop that fetch instruction from one another queue, instruction queue, and it will be handled parallelly. But there have many other topics, something like global interpreter, log, and all. So that part lock, the, Python is putting some lock in between the multiple threads, so only one thread can run at a time to avoid the confusions and all. That we will see in one another video when I am explaining about the thread, parallel programming using thread. I will do a one another um, chapter on this topic. So let's stop this one. It is getting extended too much. So let's stop this topic right now, and let's move into the next slide. In this slide, I am going to summarize the concept we were discussing previously. So this slide explains the working of subroutines. So subroutines are also called as functions or methods. So in normal way of execution, the in the normal sequential way of execution, it is calling the subroutines or methods. So generic functions, generic operations we are putting inside a method, function, or subroutine, and we can call it multiple times from multiple locations. So this is the concept of subroutine. If they have some set of repeated operations, we can put it inside a subroutine, and we can call that subroutine from any other locations. So the other concept is coroutines. Coroutine is also the same concept of subroutine, but coroutines, um, multiple coroutines can run at the same time. So in subroutine, you are calling a function here, and the control is going to that called function, and the instructions or operations inside that function, so subroutine, will be called one by one, and the control is coming back to the main uh, main loop or main string, and again the other operations are executed, and the and if they have other subroutine call or other uh, function call, it will be called. Then control will go to that function, and the instructions or operations inside that function will get called, and after that, after executing all instruction, control will come back to the uh, next line of calling function, and the flow will continue. So here also it is showing main is starting, going control to the subroutine A, then going control to the subroutine B, and so on. So this is the normal way of execution of subroutines. So in this new slide, I am explaining the next concept, that is coroutine. So previously I was explaining subroutine. So coroutine is actually subroutine itself. So multiple subroutines can work together simultaneously, parallelly. So that is the concept of coroutine or asynchronous programming. So asynchronous programming in Python is achieved using coroutine. Coroutine are subroutine only, but those subroutines can work together. So the subroutines that can work together can be called as coroutine. Cooperatively, they can work together. So it is based on concurrency. So concurrently, multiple coroutines can work, and suspend resume. So one coroutine can start the working and pass the control to the one another coroutine or to the main loop. And after some time, it can again resume its work. So this is the architecture of coroutine. So one coroutine can start its work, and after that, um, after some time, it can wait or it can suspend its execution and pass the control to other coroutines. So other coroutines can continue from that location, and after some time, the first coroutine can resume its work. So together, it have to be written in that way. So altogether, it can work. Multiple coroutines can work cooperatively. So don't focus on this picture so much, but just let me explain it. So it can initialize two coroutines simultaneously, and the coroutine can wait um, in some location of the code. It can wait, it can suspend its execution and pass the control to the first coroutine or first main loop. Then main loop can continue its execution, and when required, you can again go back. You can instruct the Python interpreter through your program to pass the control to the previous coroutine. So it will resume from where you suspended last time. So the coroutine is actually working based on starting a coroutine and waiting for some data, waiting for something, then pass the control to some previous coroutines or to the main loop, and again, whenever required, come back and resume the work. So together, they can cooperatively work. So this concept we will see how Python is achieving it. That part we will see in the coming slides. So before explaining more about um, coroutine, how coroutine works internally, the main loop, how main loop switching the control. So before explaining this topic more, let me just explain the structure of a coroutine. So here what you are seeing is a structure of coroutine. So coroutine is supported by asyncio module in Python, and they have two keywords mainly to support coroutine, that is async and await. So if there is no async keyword, it will be ordinary def, means ordinary function. It will be ordinary subroutine. So async keyword instruct Python interpreter that this is not ordinary subroutine or this is not a ordinary function, but this is a coroutine. And they have one another keyword, um, await. So await can only be used inside a coroutine. It cannot use inside a um, ordinary subroutine, or it cannot use from inside an ordinary function. So await can only be used from inside a coroutine. So await tells the interpreter to suspend or to wait the execution of the current coroutine and pass the control to um, some other coroutine or main event loop. And you can see they have two coroutines here, and what you are seeing here is a event loop. This is one of the very simple event loop. So from inside this coroutine also you can see it is using asyncio.gather. So here you are calling this particular greet coroutine three times with three different arguments. And here also we are using one other event loop. Gather is actually a event loop. So we can organize our coroutine. It is very flexible, and we can organize our coroutine as we wish. So event loop is right. This event loop asyncio.run. This is actually running an event loop. This event loop is uh, switching the coroutines. Right. It will help Python interpreter to switch the control between the different um, coroutines. And when it will switch, when the control is reaching an await statement, it will suspend the current operation. It will suspend the current operation, and it will move the control into the next waiting coroutines or to the main loops. Okay. So I'm stopping it here. I will explain this structure more in detail, uh, but let us jump into the next slide. So in this slide, I am going to explain event loop a little bit more, because it is very important to understand the event loop, its structure and all, to understand the coroutine, because uh, event loop is actually manages different coroutines. So understanding event loop is very important to understand the concurrency using coroutines in Python. So I'm going to explain different structures and of event loop. So as you can see, this is one of the very simple coroutine, and we are creating an event loop here. What you are seeing here is an event loop. So event loop is created using this asyncio module, asyncio module dot get event loop, which is actually returning this method is actually returning a loop object, event loop object, and it is calling run until complete and adding this coroutine. Actually, when you are calling task, uh, this is a coroutine, so it will not directly run uh, the instruction inside it. It will return a coroutine object. Calling a coroutine um, like this, right? Calling a coroutine like this will actually return a coroutine object. So this task method calling is actually returning a coroutine object. So it will be an argument to this run until complete method of event loop object. So this loop object is actually looping, and uh, it loops through different coroutines, and whenever an await is coming, it is switching the control to other coroutines. If they have other coroutine, it is switching control to the other coroutines. And again, one another await is present in that coroutine, it will switch the control to the next, or it will be looping. So event loop is actually responsible to run the actual coroutine instructions, wait or pause it, and when the await statement is visible, and switch control to some other coroutines. And there also, if some await is there, then control will switch back to the previous old coroutines, um, and so on. So this is how coroutine is working. So once all coroutines completed its execution, it will go to the next line, and control will be completed. So you can see this statement. This is one high level type of function run that actually internally calls, you can imagine it is internally calling these three statements. So these are two different methods of calling uh, event loop, running event loop in Python. They have many other ways also. And they have third-party libraries that implement custom event loop depending on various situations, and depending on various uh, implementation requirements. They have some other third-party libraries that support enhanced uh, event loops in Python. So in this slide, I'm going to explain a little bit more about the event loop. So I'm trying to explain what is actually an event loop, how event loop is handling multiple coroutines concurrently. So I'm not going to import asyncio. I'm not importing asyncio module here, because I want to show you how an asyncio module internally manages an event loop. So I'm not importing, or I'm not using any um, built-in event loops. I'm using my own custom event loop here. So this is a custom event loop I'm using. That custom event loop I'm initializing here, and I'm adding two coroutines, worker 1 and worker 2. You can see worker 1 and worker 2 here. Two coroutines here. I'm adding this worker 1 and worker 2 into my event loop. So as you know, when I'm calling an event loop like this, it is not like ordinary function. So when I'm calling like this, it will not execute the statements, right? These statements will not get executed. Normally, when you are calling a function like this, the statements will execute one by one. But when I'm calling a coroutine is specified by this keyword. So when I'm calling a coroutine like this, uh, it will return a coroutine instance. That's how the underscore underscore call underscore underscore, right? That special method is designed inside a coroutine. So when I am calling this uh, coroutine function, uh, it is actually returning a coroutine instance. That coroutine instances I'm passing to here, add a task, right? So I'm actually adding these coroutine instances to this event loop. So in this event loop, I have a queue. It's a list type of data structure. it is a queue actually. So I'm adding both of my coroutines, this coroutine and this coroutine, into this queue. You can see I'm appending it here. After that, I'm calling the run statement, run function, run method of my event loop. So it is reaching here. So when I am reaching here, I already have this queue populated, task queue populated. It is having all the coroutines. So I have multiple coroutines in my task queue, and I am going to run my event loop. So event loop is nothing but an loop. You can see a loop. I'm looping through all the coroutines in my queue. So this is my task queue. So I'm in this loop. I'm looping through uh, all of my uh, all of my coroutines. So I'm looping through all of my coroutines like this. So how I am doing? I have a queue and I am popping out the first queue, first coroutine. This is the first coroutine, right? Because there is a queue. First coroutine means this one. So I am popping out the first coroutine and calling it. This is how I am calling that coroutine. So coroutine instance dot send. So if you know the generator, Python generator, iterator and generator concept, right? So if you know the Python generator, new style generator, then you know that you can invoke a generator using this statement, generator.send. So that's why they have a lot of relationship between a coroutine and and a generator. Actually, a coroutine in Python is a generator that I will explain. So here I am invoking my first coroutine. So what we are trying to do in this loop, this loop manages multiple coroutines at same time. This event loop is the loop that manages multiple coroutines at simultaneously. It runs multiple coroutine simultaneously. So I'm going to explain how it is sending multiple, how it is running multiple coroutines at same time. So it is popping out the first coroutine and invoking it, task.send. So uh, this will invoke the first coroutine. So first coroutine have the print statement. So this will be executed. Next one is an await, right? So when the control is seeing this await statement, the control will be paused here, and the control will return to the next line of the caller, next instruction of the caller. So control is paused here, and here you can see the current coroutine is pushed into the tail end, and next coroutine is popped out. So this is the next coroutine, and again I am invoking using the same method. I am invoking the second coroutine. So this will be executed now. So this statement will be executed again and await. So control will be paused here. So this is how, so you can see the first coroutine is invoked and control is paused here, and next coroutine is called and control is paused here. Then again when this loop is executing, you can see this second coroutine is also pushed into the tail end. So again the first coroutine will be popped out, that will move into the first. So again I am invoking this one. When I am again invoking, it will resume from previously posed location. So it will resume from here. So it will move into the next instructions, right, from here. So you can see now the two coroutines. One coroutine is posed here, and the next coroutine is executing from this line onwards. So two coroutines are simultaneously working now, and event loop. This type of simple event loop itself is able to manage multiple coroutines at same time. And once the control is reaching at the end of any of the coroutine, uh, it will raise a stop iteration error. So when it is reaching the stop iteration, as you know, that coroutine will not be added into the tail end again. So coroutine, this event loop will run using the remaining coroutines. um, Finally, this queue will be empty and the run will be completed. So this is how it is working. This is how a multiple coroutines are working at same time. Additionally, you can see a lot of similarities, right? You can see a lot of similarities between um, a coroutine and a generator. So you have to understand when an await, um, right, an await statement is called. You can see I'm creating an instance of this class, and when an await is invoked, this await special operator will be invoked actually, and it is calling a yield statement. So await yield control instance means it will be actually replaced by a yield. So yield, when you are putting a yield inside a function, that function is actually becoming a generator. That's why you are able to pose your control and return into the crawler and resume the instruction. And again, now when you are invoking um, that coroutine, you are resuming from your previously posed location. So this is the exact behavior of a generator. So why it is showing the behavior of generator? Because await yield control is actually yield control is is a coroutine. Yield control is a coroutine instance. How it is becoming a coroutine instance? By adding this special operator. This special operator is actually running a yield statement. So when you are invoking like this, the final statement executed will be yield. So yield will replace this one. So um, that is why um, that is how this function is converted to a generator. That's why I'm telling this coroutine is actually internally um, a generator. Coroutine internally is actually a generator. So an event loop is nothing but an loop, ordinary loop. That loop handles multiple uh, multiple generators. So internally, event loop is actually an ordinary loop that handles multiple generators. Coroutines are internally generators. So you saw how these generators, because generators have the ability to pause the execution and resume. So it is pausing the execution when yield is visible, present, and it is passing the control to the caller. And when again, right, again it is invoked, the generator is invoked like this, it will resume the control from the next position. So this is how Python is implementing concurrency. So Python is implementing concurrency with the help of this type of an event loop, and that event loop manages multiple generators. So generator type of functions. So that is the concept. And when you are putting async, right, async in front of any function, it is actually internally adding this one await, and it is converting it to the function is actually converting into a coroutine. So that's all about it. We covered a lot of concepts here. So I will show a visual representation of this loop, this simple event loop in my next slide. So in this slide, I'm going to explain the working of event loop and coroutines with the help of a simple animation. So you can consider this part as a task queue. So all coroutines that have to be executed will be added into the task queue, and this task queue will be accessible to event loop. So this part we explained previously. So event loop is having access to the task queue. So task queue having all coroutines that have to be managed or that have to be run simultaneously or concurrently with the help of this event loop. So how it is working? Event loop is actually looping through this task queue. So it is going to the first coroutine and executing the instructions. As soon as it is finding an await statement, control will be returned to the event loop and the event loop will move into the next coroutine. So it is again executing this coroutine, and this coroutine will be paused when it is finding an await statement. So coroutine will be paused and the control will be returned to event loop. Same here also. Here also it will go to the next coroutine, and as soon as it is finding the await statement, control will be paused here and control will be returned to the caller, the event loop. Then again it is going to the first coroutine, and control will be resumed from the point where it is paused last time. So it will execute from that point, and if it completed its execution, then control will come back again to event loop, uh, uh, and event loop is calling the next coroutine. Here also the coroutine will resume its execution from the last point of its execution. So it is control is paused last time, so it will be resumed from that point. And if it is not completed, again if an await statement is found, then it will again pause. This coroutine will again pause its execution from that point, and the control will be returned into the next instruction of event loop. From that next instruction, it will again call the next coroutine. It is basically a loop. So it is calling the next coroutine. This coroutine will also be executed from the last post point. So execution will be resumed. And if it is again finding one another await, the control will go back here, and we know this coroutine is completed, so it will not consider that coroutine again the control will be going to this next coroutine, and so on. And once all coroutine is completed, the event loop don't have any coroutine to run more, so the control will be moving to the next instruction after the event loop. So this is how an event loop is managing concurrency using coroutines. So coroutines are actually working as a generator, and generator will be having a yield type of instruction that we already saw in the last slide. So this is event loop is actually handling multiple generators. So coroutine is actually a generator. So this is how the event loop is working. Uh, okay, so I am showing this animation here. So event loop is working like this continuously. It will be working like this. Finally, if all coroutines are completed, control will move to the next line. So if you are already clear about this event loop and coroutine, how event loop is handling multiple coroutines simultaneously, if you are already aware about these concepts, you can skip this slide. But here I am going to explain, or I am going to elaborate a little bit more about this coroutine. So that will make the working of event loop and coroutine, the architecture of event loop and coroutine more clear. So mm let me explain it here. As I already told, if you are already clear, then you can skip this slide. So let me elaborate. Let me go visually. Let me explain how it is working and all. So um, as I already told, um, as I already told, there will be having a task queue or coroutine queue. So all coroutines will be added into this task queue. So you can consider this area as the task queue area. Uh, so we are adding all the coroutines that should be managed simultaneously into that task queue. So once the task queue is populated, event loop will be having an access to event loop will be having an access to that task queue. So now let me explain how event loop is actually working. So we have three coroutines here, and each coroutines is added into our task queue, and the event loop is having access to the task queue. So it is having access to each of the coroutines inside the task queue. So first coroutine having this statements, second coroutine having this statements, and third coroutine is having this statements. So let us see visually how these coroutines are concurrently working, how event loop is managing this coroutine concurrently. So first this is an event loop. So this loop is starting. This loop is going to the first coroutine, and it is going to the first statement, and first statement is executed successfully, going to the second statement, that is also executed successfully, and the third statement, when it is reaching to the third statement, is an await statement. So when it is finding an await statement, it will pose the control here. So it is posing control here, and this one is completed successfully. As you know, this statement is completed successfully, but here control will be posed here, and after posing, what it will do, it is coming back and to the event loop, then it is going to the next coroutine. So in next coroutine's first statement, so first statement of the next coroutine, um, the first statement of next coroutine, second coroutine, right? That coroutine is again an await. So it will be control will be posed here. It will be posed here again. Okay. So again, after that, control will be going back to the next statement of event loop, and it is going to the next coroutine. So it is reaching here, and successfully completed, right? It is an ordinary statement. So since it is an ordinary statement, this one is successfully completed. This statement it will execute successfully. Then going to the next statement, it is again an await statement. So since it is an await statement, control will be posed here. Control will be posed here. Then again, um, it is returning to the event loop. So event loop fetch next coroutine. So it is a queue. So uh, the first coroutine control is going to this coroutine again, and it will resume from this point. So as you can see, this will be resumed from this point. So this is successfully executed. This line will be successfully executed. Then again, right, it is control is going to this statement. This is again an await. So again, control will be posed here. Control will be posed here, and the control. This is an await statement. So control have to be returned, and control will go to the next coroutine. So it is reaching to the next statement after the await. So this actually reaching this statement, and this statement is a normal statement, so it is fine. Then it is going to the next statement, again it is one another await. So control have to be posted there, control have to be posted there, and control is going to the control is again going back to the even loop, then going to next coroutine, and it is going to the next instruction after await. If this one is completed, right, it is checking this status here also. If this one is completed, then it will go into the next statement. So right, this statement is also completed, and uh, this statement sorry, so this statement is also completed, so this coroutine is actually completed. So it is marking this coroutine as completed, so it will be moved. This coroutine is popped out from the task queue, so this is completed actually. Once it is completed, it is going to even loop is going to and this coroutine again, and it is going checking the status of this data. If it is completed, right, then it is going to the next statement. So here um, this is also completed, and this coroutine is also completed because this entire statement is executed. So control is going back to this event loop and reaching to this one here, right. Here it is checking the await statement, what is the status of this coroutine, is it completed or not. It will, if it is completed, the status will be completed. Then if it is completed, it will go to next statement, and it will be marked as done. Then it is going to next statement. It is also an ordinary statement, so it is also marked as done. Then uh, control is going back to this coroutine, and this coroutine all instructions are done, so we can mark it as done. Then control is going to this even loop, and there is no more coroutines available, so control is going to next statement after the even loop. So this is how the coroutine is actually working um, um, with the help of even loop. So I'm stopping this slide. I hope this slide is clear. It is explaining well the implementation of even loop. Um, so I'm jumping into the next slide. So with this last slide, I am going to wind up. I am going to complete this tutorial about Python's concurrency with the help of coroutines and even loop. So I already covered all the important topics related to even loop and coroutines. So the how it is working, how even loop is switching the control between the coroutines and all is explained already. So there is no much to explain in this slide. So here they have an task queue. So before even loop is started, you can add all of your coroutine to the task queue. So even loop will pop each of these tasks one by one, and it will execute the instructions inside the coroutines. And when it is finding a await statement, so it is waiting. That means you have to wait. The control have to wait for some result from some other coroutines. So await can only followed by one another coroutine. So control have to wait there, and um, the control is going to the next um, coroutine. So they have a something like multi-level type of um, hierarchy in coroutine. So from one coroutine, you are actually creating and invoking one another coroutine. And from that coroutine, you may be invoking some other coroutine. So that multi-level architecture is also there. So, but I hope this is enough. This single level of explanation is enough to understand the basic idea about the working of um, event loops and coroutines. But in the real time scenarios, they have a multi-level hierarchy of these coroutines. So in the first level, you will be having a set of coroutines added into the event loop, and from each of this event loop, you will be calling some other set of coroutine. So whenever you are using an await, you have to remember that you are calling one another coroutine from the current coroutine. So that multi-level architecture or that hierarchy is the tree type of hierarchy is the inside this coroutines. That also you have to keep in mind. So I think I already covered all uh, components or all design details of this concurrency or these coroutines in Python implementation. So that is enough from uh, a developer side. It is enough to um, research more and understand more and to develop an efficient uh, more efficient concurrent type of application. So that's all from my side about coroutines, and yeah, thank you very much for watching.